In this presentation, I will talk about how to model the human eye using the Ansys optics tools. So first, I will discuss the motivations. Why is it important to do numerical simulations and what's their benefit for us? Then I will deep dive into a specific application of designing a multifocal contact lens for presbyopia correction using the Ansys optics tools, namely ZMAX Optics Studio and SPIOS. Finally, I will summarize the main points and draw some conclusions and open the discussion. So the human eye is our most important sensory organ. It conveys more impressions than any other sensors. And also there's a significant portion of the population which suffers from different types of vision loss. This means that there's a huge demand for better understanding of the physiology and also the anatomy of the human eye. And one way to gain that better understanding is through numerical simulations. In that case, our goal is to mathematically represent the optical components of the human eye. And due to the large complexity of the eye itself, there's a large variation in the model complexity which exists in the literature. There's models ranging from simple paraxial ones, including just a couple of surfaces, to really complex models, including aspheric surfaces, as well as gradient index materials. But there's no model which fits to every purpose or fits to every eye. Rather, the model needs to be fitted to the simulation task, which in fact can be quite diverse. The applications of numeric simulations include exploring the retinal image quality under different conditions, also predicting the vision quality, and analyzing the effect of ocular biometry on the imaging quality itself. Besides, numerical simulations can be used to design ophthalmic instruments for diagnostics, for example, wavefront sensors or OCT devices, as well as for designing corrections for patients with vision loss. That includes cataract patients and intraocular lens design for them, and eyeglasses or contact lens design for presbyopia patients. In the specific case of presbyopia, the eye loses its ability to focus to close object distances due to aging. What that means is that patients need a good way to restore the vision quality at a wide object distance range. In the recent years, there's been increased interest in simultaneous vision multifocal contact lenses as the preferred method of correction due to the demanding visual area and their cosmetic advantages over spectacles, as well as the increased practitioner confidence to fit these lenses. But what we need for that is numerical simulations again. So the Ansys Optics portfolio provides multi-scale and multi-physics simulation platform ranging from nanoscale optics to system-level simulations. On the nanoscale level, we have Ansys Lumerical, which performs full-wave electromagnetic simulations to design diffractive optical elements, metalenses, waveguides, as well as to simulate emissive and absorptive structures. On the macroscale level, we have Ansys ZMAX Optics Studio for optical design and analysis, optimization, design validation, including optomechanical tolerances as well. Finally, on the system level, we have Ansys SPIOS, which enables 3D environmental modeling in a native CAD environment, including different light sources and various sensors in order to model human vision and describe and visualize how humans or machine vision systems would see a specific image. What this means in the specific application of correction design for presbyopia, we can leverage the Ansys Optics tools with the following simulation workflow. We can start by modeling the human eye itself in ZMAX Optics Studio's sequential mode by ray tracing. Then we can leverage the powerful optimization capabilities to design the contact lens correction for the patient. Once the design is ready, we can take advantage of the optical design exchange capabilities within the simulation software and use Ansys PIOS for a full system-level analysis, including intraocular scattering as well. So to deep dive into this workflow, we can start the modeling in Zemax Optics Studio and start with the gold standard paraxial Gallstrand exact number 1 model. This model represents the crystalline lens as cortex and the nucleus, and it only uses spherical surfaces. But in order to accurately describe all the higher order monochromatic aberrations of the eye, we need to introduce aspheric surfaces into the model. Furthermore, in order to describe the significant longitudinal chromatic aberration of the eye as well, we introduce custom materials to describe the chromatic dispersion of the media. With this, we can achieve a very good representation of the unaccommodated average human eye. What that means is that it also provides a good representation of the presbyopic eye, which has lost its ability to focus to close object distances. So we can set up a multi-configuration system and change the object distance in order to analyze what the patient would see at different object distances. As we can see, the patient would have a quite good vision at far and intermediate distances. However, the image becomes completely unrecognizable for close reading object distance. So in order to restore the vision quality at a wide range, we design a multifocal contact lens, which consists of 3 concentric zones, starting with a central spherical zone for near vision, then an aspheric transitional zone for intermediate distances, and finally a peripheral zone, spherical again, for distant vision. This type of contact lens is a simultaneous vision multifocal lens, which means that the patient sees all the focused and out of focused images at the same time, and the brain learns to post-process these images. What this means is that from the design point of view, while the zones are used all at the same time, they have to be optimized separately for the specific viewing distance. So to achieve this, we can set up variables in our model, the radii and conic constant of the different zones, and we can target our optimization to achieve the smallest RMS spot size, which can be a default metric function in Optic Studio. As we can see on the images, with this contact lens, we can trade off some far vision to increase the vision quality at close object distances and therefore balance vision quality in a wide object distance range. Once the model is ready, we can leverage the easy and accurate file exchange between the Ansys Optics tools and create a full system visualization and performance analysis in SPIOS. So this means that we can set up a realistic vision test scenario, just as in the clinical trials, use the standard Snellen chart, take into account the sensitivity spectrum of the human eye, and customize our detectors to best mimic the resolution and the curvature of the retina. In order to take the model further, we can also introduce intraocular scattering in the model. Based on the literature, the most important sources of scattering in the eye are volume scattering within the lens and the cornea, as well as surface backscattering from the retina. To start with the most prominent one, we can introduce volume scattering inside the materials. We can do that by defining the protein molecules which cause the scattering effect and describe the dominating mean scattering and customizing the model by defining the radius, the density distribution, and the refractive index of those particles. With this, we can model different scenarios, such as a normal aging crystalline lens or a crystalline lens with a cataract affected. So by numeric simulations, we can visualize and evaluate, assess the performance of different scenarios. We can see what the presbyopic patient would see at different object distances, how the image quality worsens as we move the object closer to the eye. Then we can analyze how the designed contact lens would correct the vision and balance the quality between the different viewing distances. We can also see how cataract would make the image much worse, requiring for a different type of different type of correction, such as replacing the opaque crystalline lens due to the high amount of scattering by a new artificial intraocular lens. So to sum up, we have seen how to use the Ansys optics tools for creating an efficient simulation workflow for modeling the human eye and analyzing vision quality and evaluating it under different conditions. We can leverage the powerful ray tracing and optimization capabilities of ZMAX Optics Studio and take advantage of the system-level performance analysis and visualization of SPIOS. What this means is that lens manufacturers can analyze conditions and predict the vision quality in a much broader range of scenarios than it could have been done without simulations, which can lead to improving the design conditions and achieving much better correction designs, which leads to increased patient satisfaction. On the other hand, we can also use similar eye models for intraocular lens design for cataract patients. And this means that designers can optimize intraocular lenses and evaluate the postoperative vision quality even before the surgery by numeric simulations. If we take into account ocular biometry as well and customize the models based on the measurement details, then we can create personalized eye models, and that enables us to design customized correction for the given patient. Also, these eye models can be used for virtual prototyping, which means that we can leverage the models during ophthalmic instrument design, so to visualize and evaluate what the doctors would see during the actual clinical trials without building the devices and only using numeric simulations. And to close the topic, what you can do for us and what we can do for you, we develop optical simulation software. So we would like to help people to perform numeric simulations, to improve the research and development by virtual prototyping and increasing the scenarios that you can discover without building prototypes. This means that you can speed up the time to market of the devices. And what we would like to get from you is that we would very much like to hear what specific scenarios you would like to model, what are the challenges that you face during numerical simulations, and if there's any special tools or requirements for the simulations that you would need so that we can customize our product development and take that into account and introduce it in the future. And thank you very much for your attention.